So in this problems, we're going to check these two equations. And we're going to use Ehrenfest's theorem. But what is Ehrenfest's theorem? So Ehrenfest's theorem is written in this way. And let's look at the first part. So the first part wants us to verify the derivative respect to t with the expectation value of r. So what is r? So r in here actually represents, well, it could be x, y, or z. So we have to choose one because so that we can verify it. So for example, let's try x first. So according to the Ehrenfest theorem, we use x to replace the q here and write down the rest of the theorem. Okay, so now let's look at this. What is this? Well, because x doesn't explicitly involve with t, so del x del t would just be 0. So this will be 0. So we only need to care about the first term. But how to deal with the first term? We have to write down the Hamiltonian in terms of derivative so that we can simplify it. Okay, so let's write it down. So Hamiltonian is 2m divided by 1. And then px squared plus py squared plus pz squared x. Okay. Yes. And then, what can we do with this form? Well, it looks super long. So first, we need to decompose it. Well, px squared, py squared, and pz squared can be separate because, well, they're add together. So we can write it down as this, and then plus the py squared x, and then we have another term, which is py squared with z. So let's look at these two terms. So I will number it as 1, 2. So let's look at 1 first. So first, I can extract the constant, like 1 over 2m. I can move it outside so that we have this term. Well, according to the part A of this problem, we know what is pxx. Well, we know x px is equal to I h bar, so pxx should be negative h bar, I h bar. But we have px squared here. So first, we need to use something called like ABC ACB rule, which is used to separate. It's like the product rule, but with commutator. It is used to separate two things multiplied by each other. So we can't just do something like, well, this is equals to A, C, multiplied by or add by B with C commutator. So this is wrong, and we are not allowed to do that. Oh, I think I should, but anyway, so here, if we apply this rule, we have px squared, px times px x. Now we can do like px multiplied by, yes, pxx, and then plus px multiplied commutator with x, and then multiplied by px. Yes. And what is this? We already know that, which is I h bar. Yes. I h bar negative. And then what is this? We already know that is negative I h bar. Yes. So in here we have negative 2 I h bar px. Okay, so this is what we have for x, but let's look at y, because remember in here we have px squared commutator with x, we have py squared commutator with x, and also pz squared commutator with x. But because z and y is similar, because z and y are different from x, so this result will be equal to the third term, because y and z is similar in this case. So let's look at y. And all right. So here we have, again, the same constant. Yes, and also px squared with y. Everything is the same. And also we use the ABC rule again. We will have yes. So this is our results. But what is this? And also, what is this? So from previous question, we know that if two parts, like in a commutator, the first term and the second term, if they don't involve with the same variable, like y and px, like those pairs, well, they will be 0. So those two terms will disappear and this whole will just be 0. Okay, so what does this tell us? This means that the third terms here is also 0. So we have this, but 0, 0. So we only need to care about this. So the results here will be our results for the entire equation. So let me write down the full version. So dt with the expectation value of x will be equal to this. And then let's do a little bit simplification. So we can extract the constant. So negative 2 I h bar x. Okay, so the 2 would cancel and cancel and cancel again. So now we have negative px. Oh, we have m over 1 over n. And then we have a negative sign here, which shouldn't appear. So I think I made a mistake in some parts. Okay. Oh, yes, here. So when I do the cancel, I shouldn't cancel those two because I times I is -1. So here we have positive, and then I can cancel it. So yes, +1 over m, and then expectation value of px. So this results is actually the same as the results the question mentioned, which is this. Well, you can see they're the same. It's just here it use r as a combination of x1 and z. And here we have an example for x. And if we do the same for the y, here it will be py. And if we do the same for z, here it will be pz. So x, y, z, they both have the same properties. So let's look at the second part of this question, which is to prove that, well, not to prove, to check. Okay, this. Again, we can use Ehrenfest theorem. And Ehrenfest theorem tells us that d dt with p is equal to this. Okay, h, and substitute with p. And we have, oh, I should use del here. P del t. Yes, so we have this. And then let's simplify it. Again, we can write the Hamiltonian as 2m over 1 px squared plus py squared plus pz squared. But this time with p. Okay, so let's do px first, because in this way we don't involve too many variables. And so why I am allowed to do this? Because p, we can treat it as px plus py plus pz, but they're both operators. So here I'm focusing on px so that I know what happened for y and z because they're similar. Okay, so px and again plus this, but this results will again give me 0 because momentum is not explicitly associated with t. Okay, so I only need to care about this. And, well, I missed one thing for Hamiltonian, which is potential energy. My apology. And then we can separate those two terms. For example, here I have px squared plus py squared plus pz squared, and I have the potential energy, but I can remove the potential energy from inside and create another term for the potential energy. Yes, like this. And then this will give me 0. But why? Okay, so let's look at it. So the term in the left, I can separate it into 3 parts. So if we ignore the constant in front of it, which is like, so I ignore this constant, we have px squared commutator with px plus py squared commutator with px plus pz squared commutator with px. And the momentum commutator with itself is 0. And if we have square inside, we have to use the ACB rule to separate it. For example, px squared commutator with px is equal to, so we have px, so px, and then px, x, px. Okay, and this will give me 0, this will give me 0, so the entire term will just be 0. And it's actually the same for y and z, because momentum commutator with momentum itself will always be 0. Okay, so this entire terms will become 0, and the second term, let me write it down. And we don't have the 1/2m, because 1/2m is associated with the momentum. And v, yes, and I can just remove the expectation value because, oh, no, I can't do that. So let me copy this. Yes. Okay, I missed something here. So I've been thinking about, it doesn't make sense for V to be alone in the commutator. So I'm thinking, what is missing? Okay, I'm missing a momentum X component here. So now, finally, everything is all right. Okay, but what is this? Well, let's write it down. So V commutator with Px, every time when we solve this kind of problem, we need to add a function behind it so that we can see what is the effects for the derivative. So we add a function f, and then Vpx, well, let me write down px as derivative because this is a better way. Okay, great. And then we have v df dx minus the px and taking derivative to v times f. So here I'm using the definition of commutator. And then I have to use the product rule. And I can just move the v to here because v is not a derivative. Okay, so here we'll have del v del x f, and then plus v del f del x. And then let me write everything explicitly. Okay, there's a bug here. Okay, but okay, so these two things would cancel, and then this is the only thing left. So I h bar del v del x f, and they're equal, and we can just remove the f. So now we know the commutator relation for px and v is I h bar del v del x. Okay, so now we can use these results to here, right? We already showed this is 0, so we can just add it here. So it is equal to negative I h bar times yh del v del x. And the left side is d dt p x. Okay, this is x. So the results would be so there should be one negative here, so the results should be negative. Don't know why it's not negative. Think I might make another mistake here. Interesting. Okay, why it is not negative? Oh, because I have an extra negative here. Yeah, this is plus. Okay, my apology. So now I've proved that, and it is the same idea to prove for y and z because they are similar. So now finally I can make my conclusion that del del t, well, with momentum is equals to negative del v, because this is equal to okay, and then we finish the part B.